we have tiles and a lot of other things. We have the OpenGL 2 and shaders and stuff. So I've decided to target OpenGL 2.0 because I have an older machine in the basement that doesn't do anything newer that I'd like to test on someday, although I don't have that up and running at the moment. And that's about as far back as it makes sense to go in time if you want to do GLSL shaders, because anything earlier than OpenGL 2 doesn't do that, and anything earlier than Windows XP becomes complicated with respect to both Rust and SDL anyway. So that's what we're doing. So I decided to stick to baseline OpenGL 2. Hence why we have GL clamp to edge here, because GL clamp to border support is not strictly universal as I understand it. So I went with that just in case. I'll probably just put transparent tiles at the edge to make the tile map actually end in the future. But this is what it looks like right now. So, and you maybe look at this and thinking that's a lot of colorful tiles. And well, sort of, but sort of not. They're actually colorized. Because I realized that instead of drawing lots of different colors of everything, I can just draw tile set using the red and green color channels in specific ways, and then I can just multiply the red color value by one arbitrary color and the green color value by another arbitrary color in the shader, and then thus arbitrarily colorize tiles depending on, what color I want things to be in the level. That's, the power of shaders. So that's what I chose to do. So we have 3 maps for that, and in these, 1 pixel here is 1 tile here. And this one is so dark I had to apply a filter, or you can't see anything because this stores how many, the offset in this one of each tile counted in number of tiles. So for example, black means 0, 0, red is X and green is Y. So this is 0, 0, for example. And then we have, let's say, this is upside down because in OpenGL 0, 0 is bottom left, in PNG it's top left. So for example, we have, let's say this value here is going to be this guy here, right? Should be. So let's verify that. We have 6 and 4, right? So we want to go, I don't know, my mouse is being funny, but whatever. We want to go, since we're talking offsets here, we have to count tiles starting from 0, right? So we want to go to 0, 1, 2, 3, 4, 5, 6 on the x-axis and 0, 1, 2, 3, 4 on the y-axis, which is indeed exactly that tile. And if we look at the color map, we've got gray here and this light gray color here. So that's that. And for example, these corner pyramids here are just, a load of these gradient tiles and some of the from here, I think, with, gray and then one other solid color each, for example. So hopefully that makes sense. And that brings us to, well, it doesn't really, my segues suck, but why is this taking so long? Many reasons. Drawing that whole tile set and then some was one of them. I big time RTFM because I had to relearn both things I half remembered from learning OpenGL 3 at university about a decade ago, because that's the last time I dabbled in any kind of modern OpenGL. And then I had to relearn, okay, but how do I do these things in OpenGL 2 when there were differences? And I also even read the optimization manual for the old graphics card in question and some other stuff to get an idea of what's actually possible in old hardware. And yeah, did a bunch of reading. And I'm also a perfectionist, so I rewrote my code several times, and it's still a mess. So, that's life. And speaking of code, let's talk dependencies. We're still using SDL, we still have SDL3, but we now have Red Hot's graphics layer. Like I said, I'm going to lift out useful things into libraries, or factor out or whatever, so I can reuse them for other things. And I factored out loading textures and compiling shaders, because those are useful things. So Red Hot's graphics library does a couple things like that. I don't have much imagination for names sometimes, so that's what it's called for now. And we have GL46, because GLU-sys only does OpenGL 1.x, and we want OpenGL 2.0. And this is actually a crate which, for historical reasons, you have to load OpenGL functions beyond OpenGL 1. Something. And this actually wants to load everything from OpenGL 4.6 from the environment and will panic if anything isn't there. But I want to load OpenGL 2.0, and this is generated by a script, which I could probably modify to generate a GL20 that loads OpenGL 2.0, but I want to be able to load whatever I want at runtime without having several crates involved, so I wrote my own loader and just used the convenient types and enums and things from GL46. And it looks like this. It's not very complicated. We have a function array here in a struct, and we have this function that populates it, and all that does is that it takes the SDL video subsystem in, because it's hard-coded to only use SDL. It just asks for each one, where does this function live in memory, what's its address, and then we transmute that with just Rust speak for typecast or coerce or whatever you want to call it, from this generic type signature that this thing returns in the Rust wrapper to whatever we actually need it to be, to be able to call it properly with the right parameters and returns and things. And yes, you could factor out these types. GL46 does. I don't. I'm noob copy pasting. As long as you do it right, it works. So actually, I also want to show you where that goes. It actually goes in the RHGL context struct. And it is actually an option of a box of a GL funcs. What that means is box means heap pointer, basically. It's the Rust equivalent of in C mallocing the size of one of these on the heap and then putting it there. Because it's big, it shouldn't be on the stack, so we put it on the heap. But in Rust, we don't like nulls, so a box is always a valid heap pointer. But what if we're in Vulkan mode? Well, then we don't have GL functions, we have something else, probably something to do with the hash crate, I don't know yet, but certainly not these functions, right? So what do? Well, we make it an option. Then it can either be a value called none, or it can be a value called sum of one of these. And that way we can just make it none when we're doing Vulkan mode whenever we get to that. And then we just have effectively a null pointer. We don't have a big chunk of nothing on the heap for no reason. Now we get to main. We first have this function that computes the tile layer. And excuse me for jumping around, but for this to make any sense, I have to explain a part of the rendering really quick. So this is the sprite we had before, but done a more modern way. We're doing a GL draw erase. It uses a vertex buffer. We'll get to that. It basically just means the vertex data lives on the GPU. And we've told it where to find the vertices. And then we say, okay, draw a triangle fan starting at index 0 with 4 vertices. And multi-draw erase is the same, but you can do several draw calls in one function call because the tile layer is the size of the window, not the tile map, because that's more efficient. And just scrolls which tiles it displays as it scrolls along. And it is drawn line by line in triangle strips. So we do a multi-draw arrays because it's less code than writing out a bunch of these, which means we have a whole array of positions to start from, or start indices, and a whole array of lengths. That's what firsts and counts are, and vertices are the vertices. So that's what this figures out and computes, and it returns them in this handy struct here. That's what that does, which brings us to actual main, where we first get our SDL context, and then our RHGL context, and we get to specify the backend we want, but the only valid implemented option right now is OpenGL 2.0. I make a lot of plans, and if and when they happen remains to be seen, but that's the only supported option for now. And then we create our window. It's just a method on the context, and we have to tell what display we want that to be on. I just get the primary display from SDL. I have no wrappers for that yet, so you just input an SDL display. And we specify the size of the window, the title, that it shall be windowed because borderless and full screen are not implemented yet. So that's the only valid option here for now that's actually implemented. And then we want adaptive vsync, which should be working, hopefully. And then because this is a option box, we want to just get this out as a reference here. So we only have to unwrap once because that has a performance impact. And if you imagine what it would look like to have this pasted in before all of these, it would look hideous. So for sanity and performance, we just get this reference out here and hang on to it. And these are the vertices for the sprite. Still hard-coded, but they start at 0 because that means I can use these as UV values, except I flip it because, PNG and OpenGL are upside down relative to one another. But that means I don't have to pass in UV separately. I can derive them from the vertex positions. Likewise for the tile layer, actually. I derive that one in the shader from the vertex positions as well. So we only need 2 vertex buffers, one for the sprite vertices and one for the tile vertices. And what's going to go here is actually they're called names. They're more like identifiers because they're numbers, but they're called names in OpenGL vernacular. And then we need to store all the locations of all the attributes and uniforms in the shader because you can't even specify attribute locations inline in OpenGL 2. You either tell them where to go before you link, or you just link and then ask where they went, which is what I went with. A bit messy either way, and we have to declare these here because this blocks scopes. If I put all the lets here, then all these cease to exist here and everything breaks. So we have to declare these here and initialize them here. But before we do that, we create our tile layer. And if you're eagle-eyed, yes, the tiles are 32 by 32. I have 64 here to double scale them for now because I wanted a pixel art look. I'm going to have proper scaling eventually. I don't yet. So for now, this is just hard-coded to just pretend the tiles are twice as big so they draw twice as big. And yeah, this creates the tile layer that covers the entire window with tiles. And we then compile our shaders. This function just loads this, compiles it, prints errors, loads this, compiles it, prints errors, links these, prints errors, returns the result. Likewise here, And then we compute our orthographic projection matrix using a function I wrote in RHGL because I didn't want to rope in a whole crate for just one function. And it's similar, but the screen is only 1 unit in height now, which means something that's 1 by 1 is actually 1 screen by 1 screen, not 2 by 2, which makes the math a little less confusing. But it's still pretty similar. 0 is still in the middle because that's how 3D does it, so that's how I want to do it. We generate our buffers on the GPU, and then because GL is stateful, we have to bind one to the GL area buffer so we can push the sprite vertices into it, then bind the other to GL area buffer so we can push the tile vertices into it. Then, like I said, we have to ask for every single attribute in uniform, where did this thing go? So we know where to put all our uniforms and attributes later. And we can start doing that right now. Because we know the projection matrix, we already have that and it's not going to change. We can switch to the sprite shader and set that and be done with it. And then we can switch to the tile shader and also set that projection matrix. And a few other things. We set a tile layer depth because we want to be able to control at what depth the layer draws. So once we have multiple tile layers, things draw in the order they should, walls draw on top of floors and not vice versa unless we want to, and things like that. We only have one layer, but once we have several, being able to tell it what depth to be at makes sense. So we input that. And to be able to do its math, to know, UVs go from 0 to 1, but, what fraction of that is one tile and how big is the tile map? To be able to, find which pixels to read, we need these values, so we feed them in, reciprocals, because division is probably fast, multiplication is definitely fast. So just in case, we need to shift the whole tile layer because its anchor is also the bottom left. Now, everything not anchors at its bottom left. And so if it's at 0, 0, it starts in the middle of the screen and goes off to the top right, but we want to cover the whole, or the window rather, we want to cover the whole window, so we need to work out how far to the left and down to move it. To do that, we compute that here, and we input that in uniform as well, because that won't change either. And then we can set our clear color, our blending, and our culling, because those won't change. Then we can load our textures, switch to the sprite shader, load the sprite. And this function will actually analyze the PNG and figure out what the bit depth is and how many color channels it has. So we don't have to specify that manually anymore, but we do have to specify what internal representation we would like on the GPU, what texture unit we would like to bind to, and what filtering we'd like. And then we also have to tell the shader that, this is in texture unit number 0, and then we can load the tile map and the 2 color maps and the tile set, and we have to tell the shader, what texture unit those textures are in. We set GL clamp to edge for the tile map and the 2 color maps, and that's our textures done. And we still need the event pump to take input and stuff. We need to figure out how big the sprite is and how big the tile is, because the shader needs to know the size of the tile. And we also need to figure out how big the sprite is going to be to tell that shader how big that's going to be. So we declare our deltas here. We have a sprite attribute vector, which gets passed in as a uniform into that shader later. We know it's going to be, sprite size in size. And then we know we're going to want to move it half of that to left and half of that down to make it be perfectly centered. So we can set that up. And then we want to, this is just a hard-coded way to compute the default scroll value of the tile map so that it starts with the guy centered on that white thing in the middle. I'm obviously going to have some better way of dealing with that once we have an actual, game, but for now that's what we're doing. And we get to the loop. We reset our deltas like before, take our keyword input like before. Instead of moving the guy, we move the tiles to give the illusion of the guy walking around while the camera scrolls with him, but we move them the opposite way. So when you press right, the tiles go left, so it feels like you're walking right? Hence minus by, like before, the delta times 4 times the size of a pixel to move 4 pixels per frame, arbitrarily chosen. And then we can start drawing. We clear the buffer. We enable 2 vertex attribute arrays, and vertex attribute arrays, a fancy way of saying a thing that tells OpenGL where to find an attribute. We can then switch to the tile shader, update the scroll location uniform for that. We bind that buffer to the GL array buffer target, so we can tell OpenGL what attributes, in what format, at what offset it will find in that buffer. We can then issue the multi-draw arrays I talked about earlier to draw, this many triangle strips starting at these positions with these lengths. Then we can switch to the sprite shader, update its scroll, even though it's not actually moving right now, but it could be moving, and you're obviously going to have moving sprites on top of moving tiles later. We bind that vertex buffer to the GL array buffer target. We tell OpenGL where to find those vertex attributes. We draw arrays, we draw a triangle fan using draw arrays, just the one, which is one sprite for now, starting at index 0 that has 4 vertices. And we're then done. We just disable our vertex attribute arrays to leave things how we found them. And we just deal with, what if we click the close button, then we break the loop. We want to swap so you can actually see what's happening. And that's using a different function now because we weren't using the canvas. We don't want the canvas. What do you do then? If you don't want to do canvas swap, well, you do something called GL. Was it window swap or swap window in SDL? Whatever it was, that's what this wraps now anyway. And then we just sleep to the next frame. And once we terminate, we clean up after ourselves by deleting our textures and our shader programs and buffers and things. And well, that's that. Thanks for watching. See you hopefully sooner than this time. Yeah.